All right, we're going to begin a new section today. We're going to be looking at Chapter 8, Section 3. And this is still Chapter 8, so we're going to be still doing hypothesis testing. It's just going to be a different type of test here, the t-test for a mean, so for mu. All right, so a couple of things about this. Essentially, our methodology, the traditional method of hypothesis testing, and even the p-value method can both be used here. Essentially, the idea is the same. The format is the exact same thing. The only difference is essentially the way that we compute our test statistic. Well, actually, that's not even true. The way that we compute the test statistic is the same exact thing that we did in the previous section. It is, the standard form that we did. We did the sample average minus the population average divided by, well, in this case, now things are a little bit different because in this case we do not know the population standard deviation. So we only have that information from our sample. We still do this though. We still divide that sample standard deviation by the square root of the sample size. But it's that little difference, it's that little distinction, the fact that we either know or we do not know the population standard deviation. In this case, we do not know, and therefore we have to use the t-distribution, and therefore our test statistic is a t-value. But notice the very, I can't stress that enough, very similar way in which we compute the t-value and the way that we were accustomed to, the way that we were accustomed to computing the z value. So here, all we have to do is just recall the t-distribution. We're going to just go through a few exercises to find the critical t-values so that we can form our critical region in order to do the hypothesis test. And we'll also, at the same time, we'll talk about, we'll give a little preamble to the p-value method and what it says. Okay, so let's pause and look at some examples in just a minute. So we'll take a quick look at, this is example 8-8 in, of course, chapter 8, section 3. And it is located on page 442. And so here it says to find the critical t-value for alpha equals 0.05 with degrees of freedom equals 16 for a right-tailed test. Okay, so as you can see here, I said all of that just in my shorthand notation. So here we're finding the critical t-value, so that's t with a subscript of alpha divided, just alpha in this case. It's not alpha divided by 2 because it is a one-tailed test. So I've mentioned the alpha value, right, wrote that down. For the t-distribution, we need, it is based on degrees of freedom, so we need to know the degrees of freedom. And then, you know me, and I don't like to spell things. So right there, that spells right-tailed test. See? I like my spelling. It's a lot simpler. Okay, so anyhow, all right, we're gonna look it up in a minute, but the t-distribution is essentially a lot like the normal distribution. Okay, so that's terrible. We can draw it as a bell-shaped curve, and here we're thinking about a right-tailed test, so we're going to shade in the area underneath the right tail of the curve. Okay, so like that, right? Remember, the curve doesn't touch the horizontal x-axis, so there's infinite area in the sense that it's extending infinitely in the positive direction. But that area is essentially what the table in the book is going to tell us. All right, this area, we're going to be looking at a certain column in our table that makes sure that that area is always 0.05, and we're going to scroll down to our particular degrees of freedom that we need, and that's going to tell us this t value. Okay, so we'll pause and just go ahead and look that up. And so looking in table F, the t distribution, we are of course looking in the row corresponding to 16 degrees of freedom. So the first column, df, you'll scroll down until you reach 16. And then the column that we're looking in is, okay, so up at the top we have three categories. We have confidence interval, and then it says one tail and two tails. So we are in the situation where we are doing a single tail hypothesis test. It's a right-tailed test. But it doesn't matter if it's a right-tailed or left-tailed. We're still going to look at one tail, right? And then alpha is equal to 0.05. So we're going to go to the column that corresponds to one tail being 0.05. Right, so in this case, that's the second column, and we're going to go down to row 16. And so that value we found is t subscript alpha, or the critical t value. That's what the subscript of alpha signifies, is that it's tied to our significance level for our test. So it's critical in some sense. Is 1.746. 1.746. So that's this t values. 1.746. All right, so we'll talk about what we're gonna do in order to find the t value for other types of hypothesis tests, and then in just a second we'll kind of talk a little bit about the p-value method. Okay, so we're going to find, this is example 8-9, we're going to find the critical t-value for alpha equals 0.01 with 24 degrees of freedom for a left-tailed test. That's how I spelled that. So that's what that all says, right? Okay. So let's get a sketch of the distribution curve. Whoa, that was loud. It doesn't have to be perfect. Remember, it's just a sketch. And just a side note: as df, as the degrees of freedom, as that increases, our curve is going to look closer and closer to the standard normal curve. So basically, all of these are bell-shaped, and as this gets higher, when we take a larger sample, this will be a higher value, and our graph will, almost be the z-curve itself. But we have to just remember when we are dealing with the t curve versus the z distribution. So anyway, we're going to look up the t value, the critical t value, but before we look it up, let's just get an idea of what it is that we're looking up. All right, so first of all, the alpha is smaller, so this area underneath the curve is smaller. So in order for that to happen, we're going to have to be further away from the mean. Okay. And the other thing is this, since it is a left-tailed test, that's what I wrote here, right? Left-tailed test, spelled it all out. We are of course then shading in the area underneath the graph, underneath the left tail of the graph. Okay. So then we'll go ahead and look up the critical t-value. We'll go to row 24. We'll go all the way over to the column that corresponds to 1 tail alpha equals 0.01, and the value that we find is 2.492. And here it is a left-tailed test, so it wasn't critical that we sketch our graph, but it might be helpful to remind us that this is a left area, therefore our t value is over here on the left side of the graph. Remember, 0 is the mean for this distribution. So our t subscript alpha, that's what this is right here, is equal to negative 2.492. So procedurally speaking, we can just remember that if we're doing a left-tailed test, our t value is going to be negative because we're looking at the left tail of the graph. All of the values in our t table, you'll notice they're all positive values. So they're giving us the values over here. And they're saying, okay, well, you know, if it's a value that's supposed to be over here, you'll figure out how to do it. And how do you do it? Well, you just have to make it negative. So that is always something to consider. All right, let's look at the next example. So this is example 8-10 on the same page, page 443. And so here we're meant to find critical values. So here, values, plural, for alpha equals 0.10 with 18 degrees of freedom. And here, what I've written clearly, verbally, no, not verbally, with symbols, of course, is that we have a two-tailed test. Okay, well, all we do in this case is, well, almost the exact same thing. We're still going to use our degrees of freedom, so that's the first thing that we look at. The column, the very first column is the degrees of freedom. We're going to scroll all the way down to row 18. And now we're looking at the category, and not a confidence interval. It's not a one-tailed hypothesis test. It's a two-tailed test. So we're going to be looking in the second column because the value of alpha that corresponds to two tails here is 0.10. So second column, the value that we see is 1.734. So I forgot to sketch the distribution curve. So there is 1.734. Remember, the t-table, all of those values are positive. It only gives us values that are on the right side of the distribution. So it only gives us these values over here. All right. So therefore, if we're dealing with the left-tailed test, we have to remember to go back and make it negative. If we're dealing with a two-tailed test, not only do we have to remember that and look in the correct column, but then we have to remember that there's two values, and so we have one that's positive, and the other one's, well, the exact same numerical value, but just the opposite, negative. All right. So there's our critical t values, positive 1.734 and negative 1.734. So in this next one, example 8-11, directly below 8-10, we're going to be finding basically the same thing. We're going to find the critical t-values for alpha equals 0.05 with 12 degrees of freedom. And notice here, I've only drawn the right side of the distribution, so that's because it's a right-tailed test. All right, so let's switch to pretty color here. All right, so what we're looking for is we're looking for the t-value. This is it, t subscript alpha. All right, that's what that's supposed to say. All right, we're looking for the t-value. That's the value that's down here, right? Down here on the x-axis. In this case, it's the t distribution, so it's the t-axis because all of these are t-values. But what is this t-value? What's so special about this particular one right here? Well, that is the exact one that has the area underneath the curve and to the right of it exactly equal to 0.05. So that's the significance of these values that it's giving us in the table. When we are looking at alpha equals 0.05, that's saying make sure the area is already 0.05 and now find me the t-value itself. And remember, that's actually a little bit more nice, and a little nicer than how we had to use the z-table. So that is kind of the nice thing about this. All right, so anyway, we'll go right ahead and do exactly what we've done in the past. We'll look at row 12 degrees of freedom. We'll go over to the second column because that's one tail alpha equals 0.05. And we've got the value 1.782. So there that is right there, 1.782. Okay, in just a second, we're going to come back and look at the concept of area underneath this curve, and not just the critical values, but what is the area underneath the curve corresponding to any t-value. Okay, so we'll start out with, may seem like a little bit of a silly question because we were just talking about this. So let's pose the question this way. Let's just say, what is the area underneath the standard, not the standard normal curve. What is the area? So we'll start out with a little question here. May seem like a little silly question, but here's the deal. The question is this: what is the area underneath the distribution curve here? The t distribution with 12 degrees of freedom, when t is equal to exactly 1.782. What is the area underneath the curve starting from this exact value right here and so on? Well, you can't really see. I'm shading it underneath this curve in blue, but as you can tell, it's already shaded in. And that's because we already were talking about this area. It is exactly 0.05. So now let's look at this question. What is the area underneath this same t distribution curve with 12 degrees of freedom if t is equal to exactly 1.356? Okay? Well, so this is a slightly more difficult consideration because the t distribution table, table F, doesn't give us the area underneath the curve. It gives us the t value if we already set the area equal to 0.05 or some other particular value that we want to know. So unless this is one of these critical t values, we can't get the exact area. This does happen, as you might have guessed. These values that I wrote here are exactly the critical t values that correspond to this curve that has 12 degrees of freedom. As you can see, I just basically copied these values going right across row 12 in table F, the t distribution. So if we wanted to know the area underneath the curve to the right of, I'll just stop shading there because I'll just say it's the green and the blue included both together. If I wanted to know that area to the right of 1.356 underneath this curve, well, notice that that is our critical t value for one tail alpha equals 0.10. So here, the area underneath the curve is exactly 0.10. All right, similarly, okay, we won't be able to know exactly, unless they tell us one of these specific values here, 1.356, 1.782, 2.179, we won't be able to get the exact area underneath the curve. And so this is what we'll do instead if we have to do the p-value method. We'll talk about that just a little teeny bit right now. Okay, so what is this area right here underneath the curve to the right of, what did we say here? 2.179. What is this area right here? Well, looking at row 12, because any other row would be meaningless for us, scrolling across that row, we see that 2.179 is a value that's exactly in that row. And what value of alpha does that correspond to? Well, we're thinking about just the area underneath the right tail, and so that would be one tail, so that is 0.025. Okay. All right, so, and as you might have guessed here, the area underneath the curve stretching on to the right side of 2.681. As you can see for yourself, 2.681 is one of these critical values, and it corresponds to a right side area of 0.01, exactly 1%. And then finally, the last one that I included, 3.055, that area underneath the curve, that would be 0.005. Okay. All right, so let's do one last thing. Let's find the area underneath the t-distribution curve. If I give you a t value of, I don't know, let's say right here, let's erase this stuff. And just say 2.0. Boom. There it is right there. What is this area? If I shade in underneath the curve and essentially shade in the right tail of the curve beyond, everything beyond t equals 2.0. What is this area here? Okay. All right. Well, how will we address this question? Well, what we will be able to do is notice that if we go to the row 12 of the t table and look at this, we don't see this value in that row. We don't see that exact value itself. We do find values that are near it, maybe, and so our strategy is going to be to go ahead and find the two values that are closest to it on either side. So here we have the closest to it, but a little bit smaller, all right? And then over here on this side, of course, we have the value that is as close as we can get to it, but a little bit larger. So all of these values, you'll remember, 1.356, 1.782, 2.179, 2.681, and so on. All of these are all of the values, all of the critical t values coming from row 12 of our t table. So they're all our critical t values for this particular t distribution curve. And so if we want to know the exact area underneath this, this curve to the right side of this exact point, 2.0, well, we can't get it exactly, right? So if you tell me the exact p-value and it's a t distribution, I'll know that you used a computer instead of a table, basically. All right, so, well, what do? We say, well, this area to the right side here is 5%, okay? And this one, you can still see it here. The area to the right side of this one is 2.5%. Then I couldn't tell you exactly how much area this brown shaded in region is, but I know that it's somewhere in between. I know it's a little bit less than 5%, but I know it's greater than 2.5%. So there, the area for this particular t value is between these two values that we can find exactly. All right, so there is a little bit on how to utilize the t distribution table for when we are going to be doing hypothesis testing. All right, so we'll stop the video and hope that it uploads. Here you go.